Okay. Thank you. All of you have joined. Even Mr. Gaurav has joined now. Okay. Are you able to see the screen?
Yes, sir.
Yes, sir.
Okay, sir. Thank you very much. Okay. See, damage curve of the motor. Basically, every equipment is having damage curve. Just last time we saw the transformer damage curve. Same way, motor also has a damage curve. See, can you see this curve on the right side? This curve. Now, this curve is the damage curve of the motor. Okay. See, one difference. Can you tell me, Mr. Inamul, what difference you can see between this curve and our cable or transformer? Can you tell me some difference, Mr. Inamul? Sir, you're there? Okay, maybe. Okay. Pinaki Sharma ji.
So this curve is exponential, so that's one thing I observed.
All damage curve is exponential. I don't know that everything on this earth is exponential. Okay, so
No idea, sir.
okay, Mr. Gaurav, can you tell me what is the difference between this curve and our other equipment damage curve?
What I remember from, well, exactly I don't know, but what I remember from the last session was you said something about electrical and mechanical part, that up to some limit, electrical is the limit, then mechanical comes into play. This is what I remember.
That is there everywhere, electrical, mechanical. In motor, it is more, I agree, because it is rotating. But but there is one more big thing I want somebody to tell. Thank you, sir. Naveen?
Sir, maybe I think I'm guessing it because of shape, sir. Here it like that is like a straight line. This is a little bit with
No, sir. Pinaki Sharma also told that it is exponential. Shape, almost all these equipment, the shape depends because it is based on the thermal equation. Amount of heat generated, amount of heat stored, amount of heat dissipated. All of them shape will not change so much. Krishna Kumar? Okay. Gaurav, please mute, sir. Gaurav, please mute. Yeah. Krishna
So in
Kumar?
my idea, yeah, this damage curve for motors is relatively for not so much higher currents. It is, if you are seeing, starting from 1 times to 6 times, and the time is relatively more, up to more than 1000 seconds. But compared to transformer, this full load damage curve is means very much higher rate
Okay.
compared to the rated current.
But there also a high current, no? In transformer also we saw. See, transformer, let us see. Where is the transformer damage curve? The transformer also I have 25 times current for 2 seconds, 25 times current for 2 seconds. Let us go. What is the maximum current? 1800 seconds. 1800 seconds. So, Mr. Loganathan, sir?
Morning, sir. I think I'm seeing that there is the starting current is also is playing a part in this.
Yes, sir. Starting current is there, correct? But my basic doubt is the damage curve of motor and the transformer or motor and cable. Can you see some difference? That one I want to ask, sir. What is the difference? Damage curve, motor. Just from this curve itself, you can guess, sir, because it's already opened here. You can see here and you can tell.
Sorry, sir.
Okay, sir. It's okay, everybody. Thank you. I will only tell. See, Our motor damage curve, can you see there is something called rotor, stator, rotor. That I want you to make observation, because see, transformer also you have primary winding, secondary winding, but but in a motor, the damage up to certain extent is dominated by stator, later by the rotor. Just like other day we told electrical and mechanical, no? Same way. So this thing I will explain again more, but basically, you see, when you plot your this one, when you say I will, you can see this is actually. Let me go to this class of insulation. I will tell later. Let us go to you. See, there is a very nice paper by GE. I will just open that paper. I will give you the link also. You can go through that. It is an excellent paper. So you see how he has nice, and this is based on our IEEE. This one. Now you see in the beginning, it is our. You see here you have your stator and rotor, and there's one more thing is. In motor, you have one more major thing in motor is you have running and lock rotor. Transformer or cable, you don't have running or lock rotor, right? So what happens is initially the damage curve is dependent on the running, the overload condition. So you see the current keep increasing. After some time, you see the current has increased how much? Beyond 5 times, right? You can see the lock rotor. See, if I want to keep on increasing the current of a motor, what should I do? I will keep on overloading the motor, right? Keep on overloading the motor. What will happen? The motor keeps slowing down, and finally it reaches a state where the rotor gets locked. Okay, so this is that situation. Make a note of this. In the motor damage curve, you have running and you have lock rotor. Okay, these two things you have. See, when you want to do a study, you have to ask your vendor. Give me the motor damage curve. Okay, please ask the vendor. If it is a 132 kilowatt motor, vendor will not give. But let's say you are doing a study for a very big motor, your vendor will give, please ask him. Now this is the starting current, this thing I'll explain. Before that, let me open this. I'll open this paper. Able to see my screen? No. I think I have to change the share.
Yes, sir, we can see.
Able to see the screen?
Yes, sir. From PDF.
I will share this link later also. Okay. Fundamental of motor thermal model. Able to see the screen?
Yes, sir. Yes.
Yes, sir.
This is a very nice paper by GE. Please, you go through this paper today. 50 pages are there. Actually, this paper, no, why I took this paper, I'll tell you. But whatever I refer to prepare the material, I will share it. Okay, there is nothing hide, and I don't do the hiding business. Okay, so I want you to know whatever it is. So this paper, one is you can go through this table later on. What are the various kinds of failure in the motor? All that is mentioned. It is a nice study. Okay. What I want to see here is okay. This one is the motor thermal modeling. Nicely, how see all this damage curve basically from where they are developing. You have to do. It is based on the thermal modeling of the motor. And thermal modeling of the motor is based on what? See, you note down this equation. Are you able to see this equation? See, this I squared TR. What is that? Inamulji, what is this I squared TR? Mr. Inamal? Okay, maybe busy. Mr. Pinaki?
Rotor resist, it's the electrical resistance. I think it's the stator resistance. Sir.
No, basically, what is that whole term I square T into R? What is that whole term?
Heat.
Heat, what heat?
A motor loss heat.
Okay,
Like
correct.
heat loss.
Correct. It is basically the I square R loss to the motor. Correct. Okay.
Yes, sir. So, Funidar, sir, can you just, is there a mic in your room? Your voice again, there's too much echo.
Too much echo,
Just-
huh? Hold on.
Yes, sir.
Yes, Mr. Pinaki.
Yes, sir.
Maybe next class I will try to change the laptop and see. Now is
Okay,
there
sir.
any change?
I don't, little bit maybe, sir.
Okay, because the thing is, I tell you, I moved into a new accommodation, and here there is
sir.
not much items. Last time, I think this was not there. This problem. Now it is there. Okay, I will try to. Today evening, I will do with a different laptop. Let's check with that. Okay, sir.
Okay, sir.
Sir, one suggestion, sir.
Yeah.
Can we do Teams meeting from next? Because Teams, I think, little more clarity is good. I think.
Teams is a big problem. One is why I tell you. One is actually that logging for some people will be really headache. That is the reason I'm doing this, and recording. I don't know about recording there, but logging is really a headache in Microsoft Teams. Okay, sir. Okay. So, Mr. Gaurav.
Yes, sir.
So can you tell me what is this term? Say HHT-T.
So can you repeat it?
Pardon? Are you able to see the screen? This second
Yes,
equation?
yes.
Yeah.
Yes, sir.
What is this term? HTT.
As per the sheet Europa, H is running heat dissipation factor.
Yeah, it is there only. You can make a guesswork based on what is shown there. Okay.
Okay. So what it is telling is basically T dash is motor temperature rise above ambient, and H is running heat dissipation factor.
So what
So
is
this is
that?
some kind of, it is telling some kind that what is the kind of heat loss that motor can do while running at a particular, say, current or something like that.
Okay.
And
We will check with others also. Naveen, can you?
considering, depending upon the ambient temperature.
Okay, sir, okay. Naveen, can you quickly tell me what is this term?
Yes, sir. Like it's a heat dissipation when the motor is on running conditions. It is a how much rate of heat is happening.
Okay, sir, they are correct, perfectly correct. Basically, this term will tell you the amount of heat dissipated. Okay, now let me go to Mr. Krishna Kumar. Can you tell me what is this first term? C dt by dt. What is that first term, Krishna Kumar?
No, actually, no idea, sir. I think no clear idea.
Okay, sir, okay. No clarity means you are able to understand, no, what I'm asking, that is okay?
Yes, yes, sir. What is this means term you are asking? CDT by DT
Okay,
that.
okay, I will come back. Mr. Lognathan,
Okay.
Yes, sir. Yes.
can you tell me what is this first term?
Is it something what is the heat retained in the
yes.
motor?
Exactly correct, sir. You are perfectly correct. So thank you. All of you have given the answer. So basically, this entire equation, it represents a heat balance equation. In the whole world, we have balance equation, right? So this basically the amount of heat generated, please note down this amount of heat generated is equal to amount of heat stored plus amount of heat dissipated. So we basically move this term to the left side. Let us move let us move this term to the left side. Then what happens? The amount of, suppose I move this term to the left side. What happens? The amount of, so then this one, so this term is equal to sum of these two terms, 1 and 2. So amount of heat generated is equal to amount of heat stored. This is the amount of heat stored and this is the amount of heat dissipated. If you, this is basically integration equation. If you, from this equation only you are getting that. Okay, that is what I want you to remember. So if any one of you want to know how that equation came, the root is this one. Okay, that's why I took this paper. Please go through the paper. A very nice paper. Please go through anything else important here. Yeah. How thermal overload relays are modeled is nicely explained in this paper. Please go through the entire thing. I will not be going through all those things. I just wanted to briefly tell you. Okay, this paper is nice paper. I give you the link. Please go through. Then similarly, let me open one more important paper which you have to go through. And are you able to see this? Active stator winding thermal protection for AC motor. Able to see?
Yes, sir.
Yeah, this is also, see in this paper, and suppose you want to, how many of you know to run PSCAD? Anybody running PSCAD? Inaki?
Sorry, sir.
You are able, you know PSCAN, you know to run PSCAN?
No, sir.
No, okay. Okay, heard about it?
No, sir.
Okay, it's a nice software. Suppose you want to model a motor in any of the software. One way you can do is you can actually model it with the help of a resistance. See, resistance basically gives, see here, this basically shows the amount of heat generated, and this capacitance is basically the heat stored. Sorry, this is amount of I square R loss. So this, you are able to see this one, this current source with RC.
Yes.
Yeah, this basically represent motor modeling. Okay, that is one more way to model a motor. That's why I showed you this paper was. If you want to model your motor, you can also model it using this circuit.
Sir, one doubt.
Yes, sir.
For this model equivalent reference model, normally vendor will give, na, sir, for while doing dynamic studies.
Yes, sir. Vendor will give. You are correct. But small motor vendor may not give.
Okay.
Small motor vendor will tell he will not give. Big motor for sure vendor will give. Okay. So please go through these two papers. They are very good paper. And the source. Okay. Now let us go to the starting current. Okay. How many of you have done this motor starting study?
I have done.
Okay, Krishna Kumar has done. Anybody else? Anybody else done motor starting study?
No, sir.
No, sir.
Okay, motor starting study, basically what we do is, we actually, the motor is run in the simulation. Amount of current it takes is plotted. Okay, so you can see here, this is the starting current, right? Let me show this. See, this is the starting current portion, okay? And this one is the running portion. Clear? You see the starting portion is how much? 7 times. Okay. Now, can you see the difference here? And also here. What is the difference? Can anybody tell?
This number of means starting current varies, sir, from 5 times to 6 times, 7 times.
Okay, Mr. Krishna Kumar. What is that, Mr. Pinaki?
Not sure, sir. I've not come across this particular
What
curve.
is, just no, you, I have given, opened the curve in front of you. X-axis is there, Y-axis is there, something is written. Please see and you guesswork.
Based on maybe the mechanism of starting, whether you're using a doll starter, using a VFD starter,
Okay.
that curve is plotted here, I think.
Okay. Can you, okay, Mr. Pinaki, thank you. Mr. Inamul. Mr. Inamul, sir, what is there? You are not answering today. What happened? You're traveling to office or something? Maybe I think in the office. Mr. Gaurav.
So what I can see from this curve is it is telling if the motor starts at a very higher current, then it can do the acceleration phase for a lesser amount of time. And as the starting current decreases, the acceleration period increases. acceleration time period is increasing actually.
Acceleration time is increasing as the starting current.
Is decreasing.
That is, you are correct. That is a good observation. Starting current increases, starting time increases. Very good observation. Very nice observation. Okay, Mr. Naveen. We will again log in after we log out. Mr. Naveen.
Sir, sir. Maybe it's that time is decreasing as currents of percentage of current is increasing. Sir.
Current is increasing, time is increasing. Yeah, that is one answer. Mr. Krishna Kumar, what is one difference you can make out, sir? ABC curve.
Here they have given this starting current versus this motor acceleration time. In how much time it will reach this motor will reach the rated current.
Okay. Mr. Loganathan, sir.
Sir, what I can see is now when the starting current varies. Now the time it takes to stabilize come to the running stage is also when the starting current increases, the stabilizing time is less. I think that depends on the load on the motor at the starting time. Because of that.
Sir, you told starting current increases. Tell me once again, starting current increases.
No, the time it takes to reduce. The time reduces to stabilize when the starting current is more.
Time is, see, starting current has increased.
Then the time it takes to stabilize is less.
Okay, starting current has increased, time to start has reduced. Okay, sir. Thank you. I will summarize on all what you said. Number one, as you are correct, starting current increases, time reduces. Okay. So you can see there is an increase in the current, there is a reduction in the time. You are perfectly correct. Time has reduced and current has increased. Here you can see I will reduce the current, my time has increased. So inverse proportion, and that is because the amount of energy is same, something like that. That I will explain in the next slide. One more big difference I wanted all of you to tell me. Why this ABC curve? I wanted to tell what is the difference between ABC curve. See, that difference I wanted you to tell. Basically, you can see the curve A, curve B, and curve C. The difference is curve A to B, current has reduced. Curve B to C, current has still reduced. And the reason is why this curve A to B to C, the current is reduced because of voltage. This is 100% voltage is there, terminal voltage. See, okay, why this one is not. I will open a notepad. Hold on. Paint. I will open MS Paint. See, I am having my system. No? I am having my system, and I am having my motor. What happens? See here, the voltage here, the voltage here. This voltage actually what happens? This is your bus voltage, right? Suppose you are getting, let's say, transformer.
Sir, we are not seeing the screen, sir.
You are not seeing the screen. Sorry, very sorry. Now able to see?
Yes, yes, sir.
See, I am having my this source. I am having one more source transformer. Okay, well, you consider only one source, no problem. I am having the switch gear. My switchgear bus voltage is V, okay? Right, switchgear bus voltage is V. Now my motor, whatever my motor terminal voltage is there, no? Now this voltage will depend on the switchgear V. Now somewhere here, what happens, the system is overloaded. This voltage instead of being, let's say, the voltage instead of being 100%, okay, this voltage may be 90%. Voltage may come down. When the voltage reduces here, what happens when the voltage reduces here? See, what happens when the voltage reduces here is this one, okay? When voltage reduces, the starting current reduces, okay? There is an equation for that, why voltage reduces starting current. That equation, I think most of you may be knowing that, okay? The starting current is directly proportional to the voltage, and starting torque is, how is it proportional? Can anybody tell me?
Torque is proportional to V square of voltage.
Correct, exactly correct. So starting the voltage reduces, the torque will also reduce by the square. You're perfectly correct. So basically, this one you have to make observation. ABC curve is based
Sir,
on.
just one thing. These are the different starting methods that we're using. Like A could be DOL, B could be
No.
VFD. No, it's not like that.
No. Just that's the reason why I drew that picture just now is I wanted to show you that the our switchgear voltage reduces to 90% sometime 85 because of the loading of the plant. Okay, my entire plant has got loaded, and because see you have designed your plant fine, but it will not be 100% voltage, no. Then that if we have tap changing transformer, we will change the tap, we will bring it down to some voltage, that is all fine. But you have designed now after 5 years, the voltage might have got reduced to 90%. And some plants, not some, few the plants, some of them will do good maintenance. They will decide, okay, the voltage has gone down 90%. Shall I go to some add capacitors at the load side, or shall I use tap changing? So some of them will do all this, they'll do the analysis and they will improve the voltage. So some plant, okay, he will not at all do any improvement. Then what will happen? For him, the starting will be always at B. So when you do relay coordination of such a plant, please plot this B curve, okay? That is what I want to say. Before you do the relay coordination, please go check the plant voltage. Ask him to send the voltage also. Okay. Don't do the coordination without checking the plant voltage. Okay. Any doubt till here?
So this starting current and this voltage formula where we can see, sir, any standard references?
Pardon, sir?
And the torque. This starting current and torque and voltage is relation. We have any means to learn more about that, any materialist?
Yes, sir. I will share, sir. I will surely share the starting current, voltage, torque. On that some material I will surely share with you. Okay.
Sir, one more thing. One doubt. This in some means vendor drawings curves I have seen. As you said, it is 100% voltage starting and 80% voltage starting they have given normally.
Yeah.
So is this because of this this one, sir? The worst case scenario, how that motor starting current will be for studying that purpose only?
Yes, sir. 80% is given because 80 is the worst. You are only given the answer. 80 is the worst. That's why. Okay. We will log out for 5 minutes and log in back. Okay, sir. You take a break for 5 minutes.
Okay, so
Okay, sir.
In the meantime, I will convert the recording also.